In previous lessons, we learned about a set A and then the set A complement. And as a quick review, I have those two ideas pictured here. Remember that the entire box is our universal set in each case. So everything that lives inside this rectangle is part of the universal set. And then as a subset, we have the set A pictured here as this circle. And we can see that I've shaded all of set A in pink. Now the set A complement, which is written as A apostrophe, so we should read this as A complement, is by definition everything that's in the universal set that is also not in A. So it's the entire rectangle of U as long as we exclude what was part of A. And we can see that shaded here in purple. So this is just a quick review of the topic that we learned about previously, A and A complement. And the reason I want to bring this up in this lesson is from a probability standpoint, we are going to discuss this idea of the probability that an event occurs and the probability that the complement of the event occurs. Now, the main thing I want you to focus on here is notice what happens to the overall set being shaded when I combine A complement and A. So I'm combining A and A complement. And when I do this, do you see that the entire rectangle becomes shaded? So if you add together the set and its complement, you will get the entire universal set. And then phrased in terms of probability, we know the probability that an event will certainly occur is 1. So the probability that A will occur or the probability that its complement will occur, we've covered all possibilities. Either it will occur or it will not occur. So if you add together those two probabilities, you get 1. And this is going to be a very helpful formula, and because of this formula, we will be able to isolate one of these probabilities in terms of the other. So your visualization going forward is remember that this is the set A, shaded in pink. This is the set A complement, shaded in purple. And if you add together a set and its complement, you get the entire universe of possibilities. So let's introduce the idea of the probability of a complement. Suppose we have event E. The probability that E will not occur is equal to 1 minus the probability that it will occur. Written in symbols, we have this expression. The probability of E complement is equal to 1 minus the probability that E occurs, and this is a manipulation of this formula that we introduced earlier. The probability that something will occur plus the probability that it won't occur covers all possibilities. So together, when you add that, the probability must be 1, the certain probability. And notice all we've done here is we've subtracted P of E from both sides in order to get this expression. I could also, starting at this expression, isolate and subtract the P of E complement from both sides, and then I would get this expression. So keep in mind that both of these are just manipulations of this formula. Now, in some of the future examples, we're going to try to illustrate why we would think about the probability of E complement instead of just finding the probability of E itself. This next example asks us that if a single card is drawn from a standard 52 card deck, what is the probability that it will not be a king? Now, in order to help us visualize this, I'm going to bring the diagram up that we had from a previous page in the notes. We know for probability, it's always going to be the probability is the number of ways something could occur. And we're only drawing one card, so this is all the number of not kings. How many cards are not kings? And divide that by the total number of cards possible. And we know the total number of cards possible, that's our 52, because there's 52 cards in this deck. Now, I have the 52 cards displayed here in our table, take a moment and count how many of these are not kings. That would be all of these are not kings. So I could count them. I know there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cards in each of the 4 suits that are not kings. So 12 times 4 is 48. So there's 48 cards that are not kings. So my probability would be 48 over 52. Because remember, probability is always how many of the ways the thing that you're looking for could happen divided by the total number of possibilities at the beginning. So we've solved the problem. This is what I would call as a direct approach because we directly counted how many cards are not kings. An indirect approach using complement is the idea of if we're looking for how many ways you could not get a king, couldn't we take the total probability, which is 1, and then just subtract away the things that we don't want? So specifically, what do we not want to draw in this problem? We do not want to draw any of these kings. We don't want these. So add it all together, the not kings plus the kings is the entire 52 card deck. And that's why we see this 1 represented here, because it's certain that if you look at all the kings and the not kings, then together that's all possibilities in a card deck. But if we take the 1, the certain, the entire possibility, and then we subtract out the piece that we do not want, which is here, what's the probability that we would get a king? Well, there's 1, 2, 3, 4 kings out of 52. Now, in terms of subtracting fractions, if you calculated this and this right now in your calculator, you'd see they're the exact same decimal. To see that they're the same as a fraction, we need a little bit of a review of fractions. 1, to write it as a fraction where I could subtract 4 52ths, I need to write it as a fraction in terms of 52. And keep in mind, any number divided by itself is 1. If you want to verify this, take a moment and verify that 1 in your calculator is the same as 52 over 52. So these are the same thing. So we have 52 over 52 minus 4 over 52. Well, whenever you add or subtract fractions, if they have the same denominator, then you keep the same denominator. So this is still over 52. And then you subtract the numerator. So 52 minus 4 is 48. And we see we get the exact same answer whether I answer directly by calculating how many ways could I not draw a king, or if I indirectly calculate it and say, let's look at the total probability, which is 1, and then take away what we do not want to occur. In this problem, we did not want to draw a king. So if I subtract out the 4 out of 52th probability that I get a king, all that I would be left with is the probability that I would draw not a king, because I took away the piece that I did not want. So to help us kind of visualize what we just talked about here, when we did 1 minus the probability that we did not have a king, all that we're left with is what we were looking for, which is the probability, or excuse me, if we did 1 minus the probability that we had a king, got those mixed up, then all that we're left with is not a king. So if you take the total outcomes, the probability that you'll definitely get one of the total outcomes is 1, minus what you do not want, then all that you're left with is exactly what you're looking for. So this is our indirect approach. Instead of directly calculating what we're looking for, I could say 1 minus everything that's what I'm not looking for. And this method will be particularly useful when we're dealing with more complicated problems. So in our next example, we're asked 6 fair coins are tossed. Whenever they say fair coins, that just means it's 50% likely to be heads, 50% likely to be tails. So just saying it's not a weighted coin. So we've tossed 6 coins in the air and they've all fallen. We are looking for based on that toss of 6 coins, what would be the probability that we would get at least 2 heads? Now, anytime we see the phrase at least, at most, we need to take a moment and then translate exactly what does that mean in this situation. So remember, 6 coins are tossed. At least 2 in this situation. So if it says at least 2, that's the same as 2 or more. So at least 2 means that we would be okay with 2 heads or more. So we'd be okay with 3 heads, 4 heads, 5 heads, 6 heads. Now, do you think we're okay with 7 heads? Because 7 is at least 2. While 7 is definitely at least 2, it doesn't make sense in this problem because at most we were tossing 6 coins. So for this particular problem in context, at least 2 means 2, 3, 4, 5, or 6. Now, a way to indicate that this is a problem that could be used with complements is, do you see the thing that we're looking for is almost all of the possibilities? If you're okay with 2, 3, 4, 5, or 6 heads, what's the only thing that you do not want? So we do not want 0 heads or 1 head to occur. So in this case, there's less things that we do not want than things that we want. So you could approach this problem in 2 ways. You could do the direct method. I'm showing 2 different methods here, in which case we just calculate what's the probability that we have at least 2 heads, which will be the total number of outcomes from 6 coin tosses, and then at the top will be the number of ways we could get 2, 3, 4, 5, or 6 heads. Now, the indirect method, the new method that we're talking about, which is the idea of thinking through complements, is saying, look, everything together, the way we could get 0 head, 1 head, 2, 3, 4, 5, or 6 heads is the entire realm of possibilities, so that's 1. And then if I subtract out what I actually do not want, which is this, 1 minus the probability of 0 heads or 1 head, then that will be 1 minus what you don't want is what you're actually looking for. That will end up giving us the probability of at least 2 heads. Now, to this point, we've dealt with the direct approach more commonly. So since the indirect approach is new material, and in fact in this problem it will be a simpler calculation, let's do the indirect approach together. Now, I've brought up this website just to help us visualize what we're talking about. Remember, we're not looking at a particular toss of 6 coins. We're saying all possible possibilities, but hopefully this will help us kind of keep in mind what we have. So here I've got 6 coins. In the coin flip that you see on the screen, how many heads were in the 6 coin tosses? 1, 2, 3, 4. So this would be an allowable coin toss for us because we wanted at least 2 heads to occur. Let's do another flip. Does this meet our criteria of at least 2 heads? Yes, because there's 1, 2 heads shown. Let's do one more. Does this meet our criteria of at least 2 heads? No, because in this case, there's only 1 heads occurring and 5 tail flips. So this would be a case of something that we did not want to occur. Now, to help us visualize this, remember in terms of coin flips, it matters where the tail occurs. So I could get a different coin toss that's not acceptable if instead of the tails being in the first flip, it was in the second flip. Or if instead of being in the first place, it was in the third place. Or if instead of the first, it was the fourth, first, or fifth, first, or sixth. So anywhere this tail could have gone, there's 6 possible outcomes that have only one tail because it's going to move the one tail that's allowed through the 6 possible places. Now, can you visualize what would it look like if we had 0 tails in the 6 coin tosses? Or sorry, excuse me, 0 heads. If there were 0 heads, we would just get 6 tails in a row, and that can only occur one way. So now that we visualize this, let's write this down. We know that in order to get 0 heads or 1 head, the possible outcomes for the 0 heads is tails, 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 tails. That's 6 coin tosses, all tails. So there's one outcome there. For 1 head, we could have the heads in the first place followed by 5 tails. Or now we're going to move through the first, second, third, fourth, fifth, sixth position. The heads will move toward the second. So we could have gotten a tails, heads, followed by 4 more tails. Or we could have gotten tails, tails, then heads, followed by 3 more tails. Or we could have gotten 3 tails first, followed by heads, followed by 2 more tails. Or 4 tails first, heads, then tails. Or 5 tails first, followed by the heads. So for the 1 head, there's 6 ways that could occur. For the 0 head, there's only 1 way that could occur. So taken together, how many ways could we get 0 heads or 1 head, both of which we do not want? There's 7 possibilities out of the total number of ways that could occur in flipping 6 coins. That's going to be a counting problem from one of our last videos. If you're flipping a coin 6 times, we could break it up into the first flip, second flip, third flip, fourth flip, fifth flip, and then 6th flip. And each individual flip, there's only 2 outcomes, heads or tails. Heads or tails. And then we know if I could figure out the number of ways each step in the process occurs, then the total number of ways the entire process occurs comes from multiplying these. So 2 times 2 times 2 times 2 times 2 times 2. That's the same as 2 multiplied by itself 6 times, which is 2 to the 6th, 64. So 1 minus 7 out of 64. We know in order to get this into a simplified fraction, I need to change the 1 into what we might think of as our fancy 1. To subtract fractions, they have to have the same bottom number. So 1 could be represented as 64 over 64. Any number divided by itself is 1. Minus 7 over 64. We know in that case, if the denominator is the same for fractions, you keep the same denominator. And then you subtract the top numbers. So 64 minus 7. And that'll be 57 out of 64 is the probability that if we flip 6 coins, we would get at least 2 heads. To help us visualize the next formula we're going to work with in terms of probability, let's go back to some of our set theory and think about 2 sets in our universal set. So we have our universal set, which is the entire rectangle, and then I have set A pictured and set B pictured. And where they overlap, we know is set A intersect B. So what I'm shading here in orange is A intersect B. Previously, we had a formula that the number of elements in A union B, and then A union B is where both of these circles are either separately or overlapping. The number of elements in A union B is the number of elements in A, which I'll shade that here, plus the number of elements in B, which we'll shade. And notice when I shaded the number of elements in B, do we see that this middle section that is shared by A and B got counted both in the number of elements in A, and then counted again in the number of elements in B, which is why the formula continues to say minus the number of elements in A intersect B. Now, there's a direct translation of this formula, which was just counting number of elements in a set, into the idea of probability, where probability is the number of ways what we're looking for occurs divided by the total. So the translation of this idea in terms of probability is the probability that A or B occur is the probability that A occurs by itself plus the probability that B occurs by itself minus the probability that both A and B will occur. And this will be a particularly helpful formula. And that's what we see here. If A and B are any two events, then the probability that A or B occurs is the probability that A occurs, plus the probability that B occurs, minus the probability of A and B occurring. Now this was all predicated on the idea that A and B would have some overlap, but if we recall back to set theory, there were sets that had no overlap, and those were known to be disjoint sets, so let's draw that. If A and B are completely separate sets, which is the definition of disjoint, another word for disjoint is mutually exclusive. They are mutually excluding each other. Then this probability formula is simplified. So in the particular case where there's no overlap between A and B, if A and B are mutually exclusive, same meaning as disjoint, then the formula becomes the probability of A union B is still the probability of A plus the probability of B, but whenever we come to subtract the probability that we have A and B, by definition there is no overlap between these sets. So remember, if there's no overlap, there's no possibility that we would have both A and B at the same time, and the probability of an impossible event is 0. So we end up subtracting 0, but subtracting 0 doesn't do anything, so we just write the simpler formula that the probability of A union B in the case of disjoint events is just the probability that A occurs plus the probability that B occurs. Now, most commonly you will use this formula because commonly we don't know if events are disjoint or not, but if you ever have the extra piece of information that they are disjoint, then you can use this formula as a shortcut. But keep in mind this one will be the more commonly used of the two. So imagine I have this set that has elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We are going to select only one number from this set. So if it helps you kind of visualize this, imagine I have this bag, and inside the bag are pieces of paper with one has a 1, we have a 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 pieces of paper, each with one of these numbers written on them. And imagine we put our hand in the bag and only select one of the papers and then pull it out. So that's what's happening in this situation. We are looking for, based on this situation, the probability that one of the following events would occur. So our first example, what is the probability that the number I selected is odd or a multiple of 4? So in terms of solving these problems, you're going to look for some common keywords. So when we see the word or, that's a huge indication that we need to use this formula. The probability that A or B occurs is the probability that A occurs plus the probability that B occurs by itself minus the probability that they both occur at the same time. So when we read the word or, we need to begin to think and write down this formula. Now in our example, let's say the number being odd is called our A event, multiple of 4, that's called our B event. So let's just write this out. If A is the idea of being odd, look at our list of numbers 1 through 10 and write down in this subset what are the odd numbers. One, 3, 5, 7, and 9 are the odd numbers. So I've taken my entire list of outcomes and I've only written down the ones that are odd. So in fact, the probability that A occurs is the total number of outcomes, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total outcomes. I could have drawn any of the 10 slips of paper. But if I want it to be odd, I would want to have drawn either the 1, 3, 5, 7, or 9. So there's 1, 2, 3, 4, 5 acceptable outcomes. So the probability that A occurs is 5/10. Next, let's write down what's the probability that B occurs. So B is taken to be the multiples of 4. And whenever it's multiples of any number, you always start at the number in question. So multiples of 4, we start at 4. And I say, okay, 4 times 1 is 4. I've already written that down. Next, I multiply that number by 2. So 4 times 2 is 8. Notice 8 is in the list. So we write that down. 4 times 1, 4 times 2. Next up would be 4 times 3, but 4 times 3 is 12. And notice our largest number is 10, so nothing else is in the list. So the only multiples of 4 are in this set are 4 and 8. So the possible ways that could occur for us is we have our probability that we get a multiple of 4 is there's 2 ways out of the 10 ways. And now before we use this formula, I need to ask myself, could A and B occur at the same time? Well, let me re-highlight what our odd numbers are. 1, 3, 5, 7, 9. In blue, I have highlighted the odd numbers in the possible outcomes. In green, I've highlighted the multiple 4s of the possible outcomes. Is there any overlap between these two sets? No. There is no odd number that's also a multiple of 4. So the probability that A and B occurs at the same time is 0 because there's no possible overlap. So our formula is the probability that I get an odd number, our A category, or a multiple of 4, our B category, is the probability that A occurs, which was 5/10, plus the probability that B that occurs is 2/10, minus the probability that they both occur, which we know is 0. So that's why we don't really have to write the minus here. This is an example of a disjoint set A and B. So overall, the probability that one or the other would occur is 7/10. So next up, we have the same starting scenario. We have 10 numbers, of which we will select one randomly. And now we're asked to compute what's the probability that the number is even or a multiple of 3. So as soon as we see the word or, that's our keyword to tell us we should be thinking of this formula. The probability that A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that A and B occur. And remember, every time you see this in a problem, write down this general formula. It's going to do a few things. One, it's going to help you be more consistently correct in your answers. And two, it'll help you remember this formula with greater ease because the more you write it down in the right context, the more your brain is linking the probability that something or something occurs is based on this idea. Now, a recommended way of dealing with this problem is to always write down, based on your given situations, how could you meet this idea of selecting an even number? So I'm going to say the first event A is getting an even number from the list. And the total ways that I could get an even number, well, let's select those. That's 2, 4, 6, 8, or 10. Those are all even numbers within the list. So those are 2, 4, let's use the same color. So the probability that A occurs is there's 1, 2, 3, 4, 5 allowable outcomes out of the 10 possibilities, so 5/10. Next up, we'll look that we get a multiple of 3. That will be our second outcome, B. Now remember, for multiples of 3, you start at 3, and then you say, okay, 3 times 1 is 3, 3 times 2 is, think about it, and then keep going out until you've exited the list. So I'll give you a moment to write out what are all the multiples of 3 within our list of digits from 1 to 10. Three times 1 is 3, 3 times 2 is 6, which is in the list, 3 times 3 is 9, which is in the list, 3 times 4 is 12, which leaves the list because our largest value was 10. So I've got 3, 6, and 9. So there are 3 ways that B, which is getting a multiple of 3, could occur out of the 10 ways. And then particularly here, since I've been highlighting as I've selected the numbers, I hope we can see that 6 is in both the even numbers and the multiple of 3 list. So in this case, there is overlap between the two groups. One item is in the even numbers and at the same time in the multiple of 3. So since there's one item in the overlap, the idea that A and B occur is the option 6. Probability is always the number of ways it could occur, which is one way out of the 10 ways. So then to finish up the problem, we know the probability that I would get an even number or a multiple of 3 is the number of ways that I could get an even number, which is 5/10, plus the number of ways that I could get a multiple of 3, which is 3/10, minus the number of ways that I could have both at the same time, which was 1/10. Now, all of these have the same denominator. So whenever you add or subtract fractions, if they have the same denominator, you copy that denominator again. And then I have 5 plus 3 is 8, minus 1 is 7. We end up with 7/10. So in our next example, we have that Amy plans to spend 1 to 6 hours on her homework. Let X represent the number of hours that will be spent on a given night. And unlike many of our past examples where we actually had to calculate all the probabilities, in this example, we've already been given a table that corresponds to X. All of the values at the top row are the number of hours that could have been studied a night. So for instance, if she studied 5 hours, the probability that that occurs is 0.1. Instead, if she studied 2 hours, the probability that that occurs is 0.1. This is how we would read the table. Notice the bottom row is listed as the probability that X occurs, and it's already listed out. So in this problem, when we've already been given what's called a probability distribution, they've already told us the probability for the different outcomes X. We are not necessarily calculating individual probabilities, but instead we're going to answer more generalized questions. So we're asked to find the probabilities that she would spend the following options. So we're asked, what's the probability that she would spend fewer than 3 hours studying? Well, this idea of fewer than 3 hours actually must be translated in context. What is fewer than 3 hours? The possible outcomes for amounts spent studying is 1, 2, 3, 4, 5, or 6 hours. There's no other possibilities in this problem. That's all that's allowed here. So which of these numbers, 1, 2, 3, 4, 5, or 6, is fewer than 3? Well, that's 1 or 2. Both 1 and 2 are fewer than 3. So the probability that we would have fewer than 3, notice in this context, everything is naturally disjoint or separated, because if she spends 1 hour or 2 hours, there's no overlap between those two. It's either 1 hour spent studying or 2 hours spent studying. Similar to all the others, there's no overlap between 1 hour of studying and 6 hours studying. Those are separate ideas based on our table distribution. So the probability that she spends 1 or 2 in this case, since they're disjoint, is the probability of 1 hour plus the probability of 2 hours, which is, we already know the probability of 1 is 0.5, plus the probability of 2 hours is 0.1. Adding those together, and we get 0.15. So let's do the next one together. What's the probability that she'd spend more than 2? Again, this is a phrase that needs to be translated in context. Remember, the possibilities are 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, and 6 hours. Which of those meets the criteria that it's more than 2? We would be okay with 3 hours, or 4 hours, or 5 hours, or 6 hours. And each of these are distinct, because more than 2 means it has to be greater than 2. Now we know the probability for 3 is 0.2, plus the probability for 4 is 0.4, plus the probability for 5 is 0.10, plus the probability for 6 is 0.15. We add all those together. And we get 0.85. And that would be our answer. Now, in terms of some of the material that we've learned in this video, what we've done here is what I would call the direct approach. It said more than 2, and I've just calculated how that could occur directly. However, one thing to keep in mind is if we're okay with 3, 4, 5, or 6, does it make sense that we do not want 1 or 2 hours studying? That's the only things that we're not okay with. So we know if the number of things that we do not want is smaller than the number of things we could want, by our indirect approach, we could take 1, which is all the possibilities, and then subtract out what we don't want. The probability that we get a 1, which we don't want, is 0.05, minus the probability that we get 2, which is 0.10. And when you calculate that, 1 minus 0.5 minus 0.1 is exactly the 0.85 that we found above. So this was just to illustrate in this particular problem, we had 2 different approaches: calculate exactly what they're looking for, or realize if what they're not looking for is a smaller group, find what that is and subtract it from 1. Either way, you'll get the same answer. So next up we have, what's the probability that it would be more than 1, but no more than 5? A key detail here is translating what that means. So take a moment to think in context. If we have options 1, 2, 3, 4, 5, and 6, which of those meet the criteria of being more than 1, but no more than 5? To be more than 1, we can't be 1 itself, but we could be 2, we could be 3, we could be 4. Now, no more than 5 means 5 or less. So 5 would be our last option. The probability that 2 occurs, we already know, is 0.1. Plus the probability that 3 occurs is 0.2. Plus the probability that 4 occurs is 0.4. Plus the probability that 5 occurs is 0.1. And that would be 0.1 plus 0.2 plus 0.4 plus 0.1. That's 0.8. And that would be our answer here. Now, if you wanted, this is how we would say the direct approach, because we just calculated exactly what they asked for. But in writing that, I realized that what they asked for actually has almost all the possibilities. What are the only things that we do not want in this case? We do not want a 1 or a 6. So alternatively, a second way to solve this problem would be to take 1, the total possibilities, and subtract out what we do not want, which is 0.5 probability for the 1, minus a 0.15 probability for the 6, and we get 0.8 as expected, either way. So remember, 2 different ways to solve it. Choose what makes sense to you. Now our next criteria is at the bottom of the screen. How many ways can we get fewer than 5 hours? So what's allowed in fewer than 5 in context? Fewer than 5 is less than 5. So 1, 2, 3, 4. So in terms of, we're okay with the probability that 1 occurs, 2 occurs, 3 occurs, or 4 occurs. So we could add all these together. 0.5 or 0.05 plus 0.1 plus 0.2 plus 0.4, that's 0.75. So the probability that we have fewer than 5 is 0.75. And then our final question here is, what is the probability that we have 6 or fewer hours? Now 6 or fewer is 6 or less. So we'd be okay with 1, 2, 3, 4, 5, or 6 as our outcome. But notice when I start to add those together, that's the entire list. So the probability that something occurs that includes the entire list, you're certainly going to get one of those outcomes. So since I know it's the probability of the entirety of the problem, I could just know the answer is 1, because the probability that a certain event or the entire outcome could happen is 1. Or I could add each of these individual probabilities together since we were okay with any of them occurring, and I'll see that I get 1. And the probability is 1, or it's a certain event that she will study 6 or fewer hours. Now our next example says find the probability that a single card drawn from a standard 52 card deck will be a diamond, or, we see the word or, face card. So whenever we're dealing with probabilities and the words or, we automatically write down the formula. The probability that A or B occurs is the probability that A occurs plus the probability that B occurs minus the probability that they both occur. And now I just need to calculate what is probability of A, what is the probability of B, what is the probability of A and B, and then format it in this correct equation. Now to help us visualize this, let's bring forth our card diagram that we've seen earlier in these notes. So the probability that we get a diamond, I'll say that is D for diamond. We see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 diamonds. So 13 out of the 52 is the probability of a diamond. The probability that we get a face card, let's call that F. For face card, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. So that's 12 out of 52. Now let me highlight what we've seen so far. The diamonds I'm going to highlight in purple. So we had each of these 13 cards are our diamonds. Now I'm going to highlight the face cards in green. These 12 cards were our face cards, and particularly with the highlighting, do you see that the diamonds and the face cards have an overlap? Specifically, these two groups overlap with the Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds. So in terms of what is the number of diamonds and face cards, what's their overlap, there are 3 cards in the overlap. So it's 3 out of 52 cards is our overlap. Then we use our formula. The probability that I would get a diamond or a face card is the probability that I get a diamond, which is 13 over 52, plus the probability that I get a face card, which is 12 over 52, minus the probability that I get a diamond or face card, and face card, which is 3 over 52. All of these have the same denominator, so we know with fractions you keep the same bottom number. And then we do the operation said to the top numbers. So 13 plus 12 is 25, minus 3 is 22. And our answer would be 22 over 52. So particularly with problems that involve OR, I think it's very helpful to first write down our general formula for OR, and then find each of these pieces separately, and at the very end, add them and subtract them in the proper order. So in our next example, we've got 20 elective courses. Emily will, of the 20, enroll in one of the courses, and she's going to choose that randomly. Of the 20 courses, we have the following categories. 8 are considered recreational. 9 are what she would consider interesting courses. And 3 are what she would consider at the same time both recreational and interesting. We're asked to find the probability that the course she chooses will have at least one of these attributes. Now we know the phrasing of at least one must be translated. At least one means one or more of the attributes. So if we're looking for at least one of the attributes, that means we're okay if it's just recreational. Let's say R is recreational, I is interesting. It's okay if it's just recreational, or just interesting, or recreational and interesting. Because since there's only 2 attributes to be more than one of those attributes would be to be both of those attributes at the same time. There's no greater possibility since there's only two attributes being listed. So visualizing what we're talking about, when I'm saying just recreational, in this context of only recreational, or those classes that were only recreational, just interesting would be those classes that were only interesting. And then recreational and interesting is these. Now taken together, we wanted any of these outcomes, so we're adding them all together. And you see when we add together all these possibilities, we get exactly the recreational union interesting set. So we are looking for what is the probability that it's recreational or interesting, because we know that's anything that's recreational, interesting, or both. Now we know the formula for the probability that something or something occurs is the probability that the first thing occurs plus the probability that the second thing occurs minus the probability that they both occur at the same time. And I think we have information about all of these things. Remember, there's 20 courses possible. Of those, 8 are recreational. So the probability that it's recreational is 8 out of the total 20. Plus, now I encourage you pause the video, complete the problem, unpause to check your work. We know the probability that something interesting occurs, 9 were interesting, so 9 out of the same 20 courses, minus the fact that they were both recreational interesting were 3 courses. 3 of the 20 have been counted in both categories, so we subtract it once. All the bottom numbers are the same, so fractions, the bottom number stays the same. We add 8 and 9, and then we subtract 3. 8 plus 9 is 17, minus 3 is 14 out of 20. So the final topic of this video that we're going to consider is that of odds and how that relates to our probability. So as a quick review, remember that probability compares the total number of favorable outcomes to an event to the total number of outcomes. And particularly it says the probability that E occurs is the number of ways E could occur, and then it divides it by the total number of ways that anything could occur. So probability always gives you a fraction. Odds are different. In terms of odds for something, it takes the number of favorable outcomes, which is shared with probability, but instead of comparing it to the total, it compares it to the unfavorable. So odds are written number of favorable word 2, and then the number of unfavorable. So it will not be a fraction. So in the case that A of the outcomes were favorable, B of the outcomes were unfavorable, we would say that the odds in favor of the event are A to B, and the odds against were B to A. So odds in favor is favorable to unfavorable. Odds against is unfavorable to favorable. So keep these formulas in mind and let's apply it to our next problems. So suppose that Bob has purchased 12 tickets for an office raffle. There were 104 tickets sold altogether, and each ticket has an equal chance of winning. Based on this, let's answer these questions. What is the probability that Bob will win the prize? Well, he has 12 tickets. If any of his 12 tickets are picked, he'll win out of the total 104. So that's his probability. What's the probability that he will not win the prize? Well, to figure out how he'll not win the prize, 104 tickets were sold. If we take out the ones that would allow him to win, there's 92 tickets that would cause Bob to lose. So the probability that he'll not win the prize is there's 92 ways he could not win out of the 102 total ways. So these were all probability. Next, we're asked for odds. The first one is odds in favor, and the remaining one is odds against. So odds in favor is how many ways he could win, the favorable, compared to the unfavorable ways. We already discussed how many ways could he win. That's the favorable outcomes, 12 ways. 2, no longer the total for odds, but unfavorable. And we already figured out there's 92 ways he could lose. Now, odds against just reverses this. And odds against, it lists the unfavorable to the favorable. So keep in mind for probability, it's favorable ways divided by total ways, whereas in odds, it's favorable to unfavorable. And the way you find the unfavorable is you take the total number and you subtract the favorable, and you're left with the unfavorable. Now, this next problem is very similar to the one that we just did, so I would encourage you to pause the video, attempt the entire problem on your own, just to kind of check your understanding, and then unpause to check your work, and you'll see me going through the entire problem. So I do encourage you, pause the video at this time if you have not already done so. So here we have Kim's group of preschool children includes 9 girls and 7 boys. We'll highlight those, 9 girls, 7 boys. If she randomly selects one child, so of the boys and girls in the class, she is going to select one child to be first in line. And E is the event that we're saying. E is the child selected being a girl. Let's find the probability that E occurs. Well, let's, I guess, go in order of what's listed. First, what's the total number of possible outcomes? Well, the children are either the 9 girls in the class or the 7 boys. So 9 plus 7, that would be 16 total number of outcomes. Kim will select one of the 16 students in the class. Now, how many outcomes are favorable to event E? We wanted E to occur where the one selected is a girl. There's 9 girls in the class, so there's 9 ways that we could get an outcome favorable to E. How many of the outcomes are unfavorable? Well, in this particular circumstance, we wanted to select a girl as the first student in line. So if we had at random selected one of the 7 boys, that would be unfavorable to our event. So the unfavorable is 7. Now from this, we have the probability. Remember, probability is always the favorable or how many ways what we want to occur could. So there's 9 ways that it could occur out of the total 16. So our probability is 9/16. Compared to the odds in favor, well, that's going to be the favorable 9 compared with the word 2, the unfavorable of 7. Now, as we were doing those last 2 problems, you might have started to notice, oh, there's a direct relationship. If I know the probability something occurs, I could find the odds. If I know the odds, I could find the probability. And that's what's described in this box. Suppose that you know the probability that E occurs is some number A over some number B. Then remember, A is the number of ways we could get a success. B, by definition, is the total. That's just how probability works. So the odds in favor is always going to be the success, which is A, to the unfavorable, which is the total minus the success. Okay, so let's do this first example first, and then we'll talk about the second bullet point. There's a 40% chance of rain tomorrow. That means the probability that we rain is 40 out of 100. That's how percentages work. Percentages are parts of the whole, parts out of 100. So give this information in terms of odds. So the odds of rain, we know by definition in probability, they list the favorable outcomes first. So the favorable is 40, and then based on this formula, it should be 2. Okay, the total, which is 100, minus the favorable, which is 40. 100 minus 40 is actually 60. So the odds are 40 to 60. So given a probability, you could translate that into odds if you take the total number of outcomes, which is always the bottom number, and you subtract the top number, which is always the success. That will give you the unfavorable. And then odds are always success to unfavorable. Now we could reverse that. If instead we knew the odds in favor were A to B, in odds they always list the success first, and they list the unfavorable second. Now together, if you have the successes plus the failures, you've got the total options. So that's why we have the probability would then be A, the success rate, divided by A plus B, because if you take the success plus the failures, you get the total. And we see this used in our next example. Suppose we know the odds of us winning are 1 to 99,999. What is the probability that we'll win? Well, we know for probability of winning, it's going to be the success, which odds always list the success first, so I know that's 1 over. Now, this is the success for odds. This is the unfavorable. We know if I add the success and the unfavorable together, then I'll get the total number of outcomes. So there's 100,000 possible outcomes, of which one of those is favorable to us. So the probability is 1 out of 100,000. So these last two examples dealt with, if we have probability, can we then express it in terms of odds? And if we have odds, can we then express it in terms of probability?